Hello, and welcome to our video on complex logarithms. From our experience with real-valued functions, a logarithm of a non-zero complex number w should be any complex number z such that e to the z equals w. And we've seen something that does this in a previous video. Namely, if w is a non-zero number, we know that we have e to the z equals w if and only if z is equal to the natural log of the modulus of w plus I times the principal argument of w plus 2 times pi times I times k for some integer k. In other words, z must be equal to the natural log of the modulus of w plus the argument of z, where in the second line after the if and only if, I'm interpreting the right side natural log of modulus of w plus argument of z as a multi-valued or set-valued function. And so this leads us to define the complex logarithm of w as the natural log of the modulus of w plus I times the argument of w. And this is a multi-valued function, or a set-valued function, because the plus I times argument of w is not a single number, but rather a countably infinite set. And so calling it a function is maybe not the best term, because functions, of course, should take unique values, whereas here the logarithm is allowed to take infinitely many values depending on what you pick for the argument. However, we can get a single-valued logarithm by specifying the argument. In particular, we will work with the principal logarithm of w, which is log of w equals natural log of modulus of w plus I times the argument of w. Here we have three kinds of logs floating around on our slide. We have ln, the natural log from real variable calculus. We have lowercase l log of w, which is the multi-valued or set-valued function. And we have capital L log of w, which is defined with the principal argument, not just any argument. Sometimes people will use the word branch related to the logarithm. A branch of the logarithm on a set D, that's a subset of the complex plane not including 0, is a function f from D into the complex plane such that e to the f of z is equal to z for all complex numbers z in D. In other words, this function f sort of inverts the complex exponential. And we can always get a branch of the logarithm by working with the principal logarithm, but we could get other branches of the logarithm just by specifying the argument to take values in some particular interval, rather than letting the log be defined by all of the argument values.